Yinhuai is a second-year PhD student at HKUST under the supervision of Professor Ping Tan. His research interests focus on humanoid local manipulation. And now, welcome again, Yinhuai, and I'll pass the floor to you.
Okay, thank you, Tianyuan. Today I'm very happy to share our recent paper, HumanX, toward agile and generalizable humanoid interaction skills from human video. I am Yinhuai Wang. Yeah, so I do not introduce too much. My research interest focus on interaction imitation, which I began during 3 years ago from our first project, Face HOI, uh, to Skill Mimic, and then Skill Mimic V2, and some other works are in submission. So I my research interest is all about how to make humanoid robot to imitate human interactions with the world. Yeah. Okay. So humans are interacting with the world every day, from sports, household works, and the cargo delivery and factory. Yeah. So we want to make humanoid robot to do these interactions just like human do. But how we can make it? Recently, we have many technology breakthroughs in humanoid robots. It begins in the locomotion imitation area. A typical example is the ASAP, which imitates a single human motion, uh, and then twist representative work that can imitate generalizable human motions through teleoperation. And later
Hi,
on,
Yinhuai.
we,
Hi, did you share the screen while like playing the slides, or you just like
yeah,
put the slide on the first page and then keeps?
okay,
We can only see the first page.
Yeah, yeah.
okay. So let me. Now can you see the page
Yes,
changes?
yes,
Yeah,
we
it's
can.
good.
Okay. So here is my research interest, and we are here. So locomotion imitation is, I think, is a foundation for humanoid robot to do further interactions with the world. Yeah, and this area has made significant progress. However, those works are mainly focused on local manipulation, not too much about interaction. So, how to make humanoid robot to interact with the world? I think there are mainly two ways to achieve that. The first paradigm is first we need to have a very good teleoperation controller that can control the humanoid robot through teleoperation. Yeah. So if we can have such a controller, we can teleoperate the robot to interact with the world, and we can collect data and then use those data to train a behavior clone controller. So we can have a hierarchical control uh, to use the BC controller to control the teleoperation model uh, to indirectly control the humanoid robot. Yeah, and that is how the Human Plus and Omni H2O does. Yeah. Uh, and for Sonic is similar. Sonic uses a pre-trained VLA as an interface to control the teleoperation system. Yeah, but this kind of control paradigm have inherent limitations about the interaction robustness, and it is very difficult to interact with very high dynamic objects. Yeah. So if we want to, if we need the humanoid robot to interact with the world very agile and dynamic and robust, we need a new paradigm. Yeah, that is some recent works try to do. A typical example is the face HSI, which uses AMP reward to imitate the human motion, while they designed different task rewards for different interaction tasks, such as pick up a box. They design a task reward to pick up the box. Yeah. As for other works like humanoid goalkeeper and hitter, uh, they treat the interaction task simply as moving the any factor to a certain places, a certain point, such as it will first estimate the landing location of the object and then command the robot to move to that position. Yeah. So basically, these methods are task specific. Yeah, they need to design the specific rules or task rewards for specific tasks. Yeah, so it is not very general. Yeah. If we want to pursue generalization, we in our prior work, Face HOI and Skill Mimic, we proposed the paradigm called interaction imitation, which means we if we have a HOI motion data, which means human object interaction motion data, we have the human motion and the object motion. We can learn the policy in simulator to mimic both the humanoid motion and the object motion. And also, we need to model the interaction as a human-object relative interaction and context status. Yeah. So finally, we can train a model which can mimic the human-object interaction. Yeah. However, this was only in simulator, and we can see that the humanoid robot here is not like what a real robot like. Yeah. So if we want to achieve this paradigm in real world robots, it faces several difficulties. The first problem is about retargeting. Yeah. So we need to retarget the human motion into a humanoid robot, which is very difficult considering we have a additional object. Yeah. And another problem is about the symmetry gap. Yeah. And the third problem is about the data source. Yeah. How do we get enough HOI motion data? Usually, if we want to get very high quality HOI motion data, usually we need to have a mocap system to do the data collection. Yeah, which is very expensive. But can we have a more convenient way to do that? So to solve those problems, we propose HumanX. HumanX have two core components. The first is XGene, which can directly convert human videos into humanoid interaction data. Yeah. And the core difference between XGen and the previous works is that in XGen, we do not need to explicitly modeling the human object interaction data. Yeah, we directly generating humanoid interaction data. Yeah. Once we get the humanoid interaction data, we can design the interaction imitation framework to imitate those behaviors to learn the generalizable interaction skills.
Can I ask you a question?
Yes.
Yeah, so I guess for the skill mimic, what is the observation space and what's the action space?
Okay, for skill mimic, the observation space is only the proprioception and the object status, and plus a skill label. Yeah, one skill label encoded in one hot.
Oh, I see. And the action is, I guess, the XYZ movement of the hand.
The action is just like the normal WBC controller. Yeah, the it's the position of the every joint. Yeah.
Got it. Okay. Thank you.
Yeah. Okay. So now I will introduce each components separately. First, I'll give a brief introduction about the Xstream pipeline. So first, we can utilizing existing tools to transform the human video into human motion, which is very mature. We can use GM, yeah. And the second step is we can retarget the human motion into humanoid motion. So those steps are quite mature. Yeah. For example, the GMR are very useful tools, and in this work we use GMR to do the 1, 2, 3 steps. Yeah. So the core steps lies in the right parts. Yeah. The very important step is about how to get the object mesh and the object anchor configuration, which means the object and anchor relative relationship is, we can see this relationship is unchanged between human object and humanoid object. Yeah. So there are a lot of ways to acquire the mesh and this configuration. For example, we can use SAM3D to estimate the object mesh and hand object poses. Yeah. And or we can manually define the hand object poses. Yeah. And the second steps, and the next step, once we determined the object anchor configuration, we can generate the object trajectories from the anchor. Yeah. Which means we can generate the object trajectories from the human motion now. Yeah. Okay. After that, we can get a naive humanoid object interaction data. Yeah, but the context status may be imperfect. So we need to optimize the context. And these the 4, 5, 6 steps are all about the context stages. Yeah, the context stage. So for the non-context stage, we use physical simulation to generate the non-context stage object trajectories, such as if if the data is about catching a flying basketball or kicking a football, uh, during the non-contact stage, the object does not contact with the humanoid. So we can use the physics simulation to simulate the object status. Yeah. And finally, we can concatenate and interpolate between these stages, and finally to get a full interaction trajectory. Yeah.
I have a question.
And during our
Sorry.
okay.
How do you get the object initial state?
Yeah, we have two ways to get the object initial states. The first is, for example, if we take a typical frame from the video, such as this frame, we can use SAM3D to estimate the object mesh and the hand object relative relationship. Yeah.
Yeah, but I mean the global position in the space. Oh.
Yeah. You use SAM3D can get the global position of the human and the object. Yeah.
Okay.
Yeah.
Yeah,
that is.
I also have a question. Do we assume we always assume like the object is in between our hands? So this is the only config that we can get, or we can extend this pipeline like very easily to other things. For example, one hand is like holding a bottle, while another hand is like pushing a chair. For that case, like how will you do the contexting?
Yeah, I think it's possible, but we do not consider the dexterous hands yet. Yeah, but my previous work is about is about purely synthesis hand object interaction data. Yeah, so most of the inspiration was from our prior work. Yeah, so I think it is very possible. Yeah, very possible.
I see. And do you, when you use like the physical based simulation, do you train RL or?
No, we do not need to train RL. Yeah, it's just like throwing the ball into the air in the simulator, and you record the object trajectories. Yeah.
I see. Okay.
Yeah, and it is very interesting. If you want to catch a flying ball, and the ball can exactly fly into your hand, you can reverse the trajectory. Yeah.
Yeah, I think that's a good point. Yeah.
Yeah.
But I still have a question about like if we so right now I feel like the hand is more like a bow or more like a fake hand. But do you consider the grasping like the grasping just consider as a gripper you have open and close. No need to be dexterous.
Okay. I think it is also feasible. Yeah.
I see. Then based on the mesh of the object.
Yeah. So, for example, if you want to consider five fingers dexterous hands, actually the hand object grasp pose can be easily synthesized. Yeah. So basically, you can synthesis a diverse hand object interaction like that. Yeah, you can have different grasp configurations, and all these configurations you can synthesis. Yeah, you can use force closure rules to massively synthesis. And once you get the hand object configuration, you can use our pipeline to synthesis the full interaction trajectory. Yeah.
Yeah, makes sense. But the full trajectory is like ideally it should be considered dynamics, but I feel it's still somehow like a kinematic trajectory because it didn't consider like the tracking arrow of the lower controller side. For example, in order to like lifting a box, even though you have a perfect reconstruction, you still assume like the low-level controllers can very precise and very stiff. But for most of cases, you need to move your arm like a bit inward in order to generate sufficient force. That's how you solve that.
Okay, that's a very good point. Yeah. In our previous works, I guess let's see. Yeah, in our skill mimic V2, we find we also find that problem. That is, if you have a very low quality interaction data, yeah, we can also learn the perfect interaction. Yeah. So the one benefit of our interaction imitation paradigm is that our reference data do not need to be perfect. Yeah. So the learning system can learn a perfect and physically plausible interactions through reinforcement learning. Yeah. As long as your data are not very bad quality.
Yeah, sure. RL can do that, can solve that.
Yeah. Okay. So another point you may need to pay attention to is that we can augment several stages during the data generation. So which can make us generating diverse and massive data. For example, during the contact phase, we can replace the object mesh into different shapes. And our false closure and contact observation can make sure this augmentation is physically plausible. Yeah. And similarly, we can change the object sizes and even the object pose. Yeah. So finally, we can generate diverse interaction data from one video. And this is for the contact phase. So for the non-contact phase, we can also have several augmentations, such as we can, for example, for the badminton hitting task, we can generate different trajectories that hit at the same point. Yeah. So the robot can learn to hit different trajectories. Another example is in the basketball shooting task, we can generate basketball that shoot at different distances. Yeah. And with this data, we can train a humanoid robot that can shoot to different distances. All of this can be achieved from a single video. Yeah, I think which is very effective. So finally, we can see an example of our full trajectory. Yeah. Okay, so this is about the XGen pipeline. And now we will dive into the XMimic pipeline. So XMimic is a two-stage training framework. For the first stage, we train a privileged teacher policy, which observe the privileged observations such as the object states and the reference data information. Yeah. Such as the tracking target of the body position. Yeah. And the OT denotes the proprioception, and the ST denotes external perception, such as the object perception. Yeah. So the pipeline, so the training is quite simple. All we use is a interaction imitation reward with some regularization terms. Yeah, we do not need any task-specific reward. So all of the skills are used the same imitation reward. Okay, when the teacher policy is trained, we can use stagger and reinforcement learning to train the student policy. Yeah, so the student policy do not need the privileged observation such as the tracking target. So and the external observation is optional, which means we can have the object perception, or we do not need. If we don't have the object perception, it is also feasible for some tasks. Yeah. So the reward is the same as the stage 1. Yeah. So finally, we can get the student policy, which can directly deployed in the real world. Yeah, and our policy runs at 100 HZ. Yeah, and as I said, our system supports two modes. The first mode is we can ignore the object perception and use the proprioception to indirectly perceive the contact status of the object. Yeah. So this mode is very simple. And another mode is that we can use mocap system to perceive the object status. Yeah. And here is some details about the observation and rewards. So for the rewards, most of the rewards is derived from the locomotion imitation works, such as those body imitation turns. Yeah. So the difference lies in the interaction related terms. The first is the object reward, which requires the simulated object status resembles that of the reference, including the object position, or optionally we can have object rotation. In the basketball case, we do not need the rotation reward. Yeah. And another is about the human object relative motion reward, which is very important to preserve the interaction quality. Yeah, if you want a very natural interaction, this term is very important, especially in the basketball skills. And the third term is about the contact reward. Yeah, we formulate per frame the contact status, which defines which part of the humanoid need to have contact, and which parts do not have contact. And this contact status need to be aligned between simulation and reference. Yeah. And which is also very important if you want to learn a very natural interaction. So there are some other tricks which is very useful during the training. The first is the disturbed initialization during training, which means if you have the green line is the original data. Yeah. So if you learn only one data, it is very easy to overfit to that data. So we need to introduce some disturbance to the initial position of the object so that the trajectory can be changed in a small area, yeah, to avoid overfitting. And there is another problem may encounter, that is, if you disturb the object position too far, the humanoid may not hit the ball, yeah, so it may fail. So we introduced another trick which called interaction-based early termination, which will check the interaction, a relative motion between the object and the body key point. So if the relative position relative position arrow is bigger than a predefined threshold, and the whole episode will be terminated. Yeah, this is very important to prevent overfitting. Yeah. So finally, even if you disturbed the object initial states, the humanoid will tend to maintain the relative motion unchanged. Yeah. Okay, that is the necessary technical details. So here we comes to the experiment parts. So we have three tasks in the simulation experiments. The first is basketball catch shot, which means a basketball will come to, we're throwing into a humanoid robot, and the robot will catch the ball and shoot into the basket. Yeah, and the badminton hitting task is simple, which means a badminton flying toward a humanoid, and the humanoid hit the ball. The third task is about cargo pickup, which means a cargo is randomly placed in front of the humanoid, and the humanoid will come to the cargo and pick it up. Yeah. So we compare three methods. One, the first is skill mimic, then omni retarget, then HDMI, and we apply our method four core components. The first is the disturbed initialization. Yeah. The second is the interaction-based determination, and the third is the exchange data augmentation, and finally is about the teacher-student two-stage training framework. So we can see that our base method outperforms the prior works significantly, and our core components contribute to the final generalization success rate very significantly. Yeah. And there is the illustration about the generalization. Yeah. So the yellow trajectory is the basketball trajectory, and the green is different basket position, target position. Yeah. So we can see that the humanoid robot can shot the basketball precisely into different basket positions. Yeah. It is worth noting that all of these skills are learned from a single video. Yeah. So we only need a single video to learn a generalizable interaction skills. Now, this is the badminton hitting example. We can hit badminton from flying from different positions, and we can pick up cargo from different positions. Yeah, so we can see a very strong generalization performance. Okay, and finally we come. Okay, some problems happened. Okay, we come to the real world experiment results. So the first is about the no external perception mode, which means we do not use any external perception for the object. So the robot percept the object status through proprioception. Yeah. This is the basketball term. And this is layup. And this is dribble. Okay. But in this mode, the robot cannot operate continuously. Yeah, because once the object lost, once the object are not in contact stage, it cannot feel the object. Yeah. So if we want to have continuous interaction with the object, we need to involve mocap system to sense the object status in real time, such as we can throw in the ball continuously to the robot, and it can throw back to the human. Yeah. And yeah, and we can also observe some interesting phenomena. Yeah, if the human catch the ball jumps, and the humanoid will react in real time. Yeah, but only when you really throw a ball into the humanoid robot, it only react to the it only react to the ball. Oh. Okay. Here is the cargo pickup example. So if the human take away the cargo, the robot will react in real time to pick it up again. Yeah, which is also very interesting. And we can even change the object significantly in real time, and the robot are robust enough to handle this situation. And another interesting case is about the fighting. Yeah, we can see that the human pretend to attack, and the robot reacts to that action. Yeah. And it only fight back when the human really hit the robot. And here is the football kicking case. Actually, it can kick for more than 20 times. Yeah. So it is very I think it is very robust enough to make that. Okay. That's all. Thank you.